But remember, the mean value property says that we can go back the other direction too. We should be able to say, if I have a mean value property, then I am a harmonic function on that ball. Okay, so that's the last part of the proof, is to go back the other direction. So conversely, let's suppose that U has the mean value property, and the mean value property is just that it's equal to its mean over any ball where it's defined. Okay, then phi prime of r, okay, is going to be equal to r over n, the integral average over bxr, Laplacian of u dy. Okay, we know that this is equal to 0 because we already proved it. Okay, now since phi of r equals u of x is going to be constant in r, okay, so then that means that the integral average over the ball of u dy is equivalently equal to 0, okay? And then letting r go to 0, we get that the Laplacian of u is equal to 0, okay? Since the Laplacian of u is continuous in the domain omega. Okay, so that's our proof. So essentially we were able to take this derivative, right? And we applied, essentially a Green's identity to that derivative in order to get this result. And because this integral is 0 for any r, we know that we can take r to 0, and we just get back the Laplacian as 0. Okay, so we can go either direction. That's the mean value property. What are the consequences of this mean value property? Okay, well, the first consequence is what's called the strong and the weak maximum principle. And which we'll talk about shortly, okay? But this is related to maximum principles that we've already talked about for the heat equation. Once we have the mean value property, we can actually prove a uniqueness theorem with that, or we can use the maximum principle to prove uniqueness, okay? This also gives size estimates on harmonic functions, okay? Because you'd imagine if you have a bound essentially on, if you know something about how a ball around you, how the values in a ball around a certain point are going to vary, they all need to co-vary in a way essentially so that that average still remains at the value of the interior point of the center point of that ball. Then you can sort of, chain balls together essentially to tell you something about how fast a harmonic function is going to change. And the last consequence of this is what's called Liouville's theorem, okay, which essentially says that only bounded harmonic functions are constant, okay? So all the constant functions you can think of, they should satisfy, being both bounded and harmonic. Okay. I'm going to take a breath there. Are there questions about the proof or anything that I've said so far?
Um, this, I know this is related to analytic functions in the complex plane, um, but I'm having, and I see a lot of the similarities, but I'm having trouble sort of sussing out what the differences could be. I know for one, this is like higher than 2 dimensions. Um,
Right.
but are there some other obvious ones that I'm missing?
Um, yeah, so I mean, I think like analyticity, um, to have analytic functions in the complex plane, um, I think is it not a milder condition than being a harmonic function?
I think it's equivalent.
It's equivalent.
Hmm.
Okay. Yeah, I mean, then it may be in this case that if you're talking about a Laplacian in 2D, uh, then there's not really much. I mean, there's essentially it's a near equivalent condition in this case, right? Because um, as long as you're saying that well, it's an analytic function on some bounded domain, and that's equivalent to saying that you have a harmonic function on some bounded domain, then immediately the mean value property should follow from that. So I yeah, I don't see any main differences other than that, yeah, this speaks to dimensions beyond just the complex plane. So yeah, I think you're safe to sort of map those two things in that way. But yeah.
For going the converse direction on our proof, does
Yeah.
the R over N not screw things up when R starts going to zero, like already driving that ball integral to zero, or no?
Uh I mean it's fine, right? Because yeah, I mean it's you know that I see what you're saying here. So you're saying if I take the limit as R goes to zero, does this not, how do I then know
Right, or I guess,
that this extends properly in this case, right? That it's
yeah.
not the reason that this is going to zero, it's just that it's already equal to zero. Um, yeah, because this is zero. It says that this thing is zero everywhere. So if I divide through by R, I think it's okay because we're saying that it's this expression is zero everywhere. And so yeah, if I wanted to be more careful about it, then I could sort of take R smaller and smaller and smaller and say that yes, this expression is still equal to zero. It's not like this expression here is tending to zero as R goes to zero, but rather I know that this expression is zero for any value of R. And I think that because this expression is zero for any value of R, then this issue of the limit as R goes to zero, you can handle that. But yeah, this proof sort of glosses over that.
Okay.
Yeah. Okay. Okay, so I think and we have like 3 minutes left. I try to go sort of slowly through that proof. So I'll just introduce the maximum principle, and but I'm not going to prove it in this lecture. I'll get back to it in on Monday. So let's talk about kind of the next tool that we have for analyzing solutions to Laplace's equation. So if we let omega be some subset of Rn, okay, and we let it be open and bounded, and we suppose that U is C2, and on the interior, and that it's going to be just continuous, at least on the closure, and we make it harmonic in omega, then the max principles are the following. So the weak one says that the maximum of x over the closure of omega is equal to the max on the boundary of U, okay? Just like the weak one for the heat equation. Whereas the strong maximum principle says that if omega is connected, then either U is just a constant on the closure, or U of x is strictly less than the maximum that we have on the boundary, okay? Basically for any x that lives in the interior, okay? And so we're actually going to use the mean value property to prove this. We'll do that on Monday. But the idea is that we can essentially sort of tile the interior with all of these balls and sort of take them up to the boundary of omega, and essentially use the fact that we have this mean value property satisfied to say that the only way you can get kind of a maximum point is to be on the boundary, because then you can't take a ball around that point because it would go outside of your